Hey all, my name is Chris Evans. I'm a data science engineer here at AdRoll. I've been working here about 2.5 years. So this talk is sort of what I would have liked to tell myself right before I first started. So prior to coming to AdRoll, I was actually in academia doing theoretical math research, i.e. very far removed from actual engineering practices and real world messy situations. And so today I'm going to talk about our actual implementation and infrastructure for our click prediction algorithm, or click prediction model. So we at AdRoll, if you didn't know already, are in the business of showing people ads online. And in particular, we want to show ads to people who are likely to click them. And as such, we need to predict how likely somebody is to click them. But let's get into some of the details. So first of all, we use what's called real-time bidding. So the way real-time bidding works is that whenever you visit a web page, in case you didn't know, behind the scenes there's a little mini auction that takes place. In fact, it takes place within 100 milliseconds, during which various people compete to get to show you their ad. And okay, so people bid how much they're willing to pay to show you their ad, and the winner gets to show you the ad. So we participate in these auctions, and as such we need to bid intelligently. We want to bid more when we think you, the user, is likely to click on the ad or go on to buy the product, which we call convert. And we don't want to show ads to bots. And we also sometimes have to deal with weird auction dynamics. It's not always the case that, well, certainly whoever bids the highest wins, but what you actually pay can vary from auction to auction. So there's various bidding strategies. A real simple bidding strategy would just be to bid a flat amount, and you can interpret that as sort of an impression. That's or the ad tech slang for an ad. So you just figure, well, an ad's worth $1 to me, so I'm going to bid $1 on every ad. If you bid a flat amount, this gets you the most ads for your money. But like I said, we care, and our customers who work with us care more about clicks and conversions. So a better bidding strategy is the following. So we bid a constant times the probability that someone clicks, i.e. the expected value of the ad if you only value the click part of it. So you can think of this VCPC as the value of a click, and PCTR is the predicted click-through rate, i.e. the probability of a click. And so this strategy here gets you the most clicks for your money. But of course, the key ingredient here is figuring out the probability that someone's going to click an ad. And okay, so how do we compute that? Well, if you are in the theoretical world, this sounds very easy. You say, well, it's just a binary classification problem, right? So we have data, labeled data. It's supervised learning here. So we have, say, a 1 or a 0 if they clicked or not when we showed them the ad, and then we have a list of features. So maybe there's somebody in the US who clicked, and then maybe somebody in Finland is a hacker and doesn't want to click on our ad, so we don't want to throw any money their way. And so, yeah, okay, this is kind of simple. You say, well, use a logistic regression or something. But it's really not so easy at the scale we operate at. So what are some of the issues we face? Well, first of all, we have terabytes of impression and click logs to train over. So we have tons, big data, as people like to say. Furthermore, this is a real-time system, and like I said, we had a 100 millisecond window to return our predictions. And we need our models to be fresh. We have new advertisers coming on all the time, so we want to be able to have the model work for them as well. So we want to train new models frequently. And of course, since we're training all these models frequently and setting all this stuff up automated, we want our infrastructure itself to be automated so that we don't have to have some human going and refreshing the model every once in a while. So what are some solutions to these problems? So we use downsampling. So we have, it turns out people don't click that much on ads. So we have many more ads than we have clicks, i.e. many more negative labels than positive labels. So we can actually throw out a fraction of the negative. So we'll keep all the positive labels, but we throw out a large fraction of the negative labels. And of course, that biases our predictions, but we can account for that at serve time, so it's not an issue. We do lose some data in this process, but it makes up for it by being able to train the model further. And again, since we keep all the positives, we do get the real key signal that we're looking for. Then we also use this thing we call the features graph. This is actually the idea of a former engineer, Benoit. The raw features we have look something like what I showed back here. Just the country, well, actually, we don't even get the browser. We get the user agent, for example, right? So we have at the top of this features graph, when we parse a request or a bid request, we have, for example, the user agent of the user, and we have the timestamp and the country. But we want to actually train our model on more specific features, right? Like timestamp has incredible granularity. We don't care about that so much, but maybe we care about hour. User agent itself we don't care about, but we want to extract the OS. So we build this graph in the computer science sense, where we populate first the raw features, and then from them, they propagate down the graph and fill out all the other features. So for example, from the user agent, we get the OS. From the timestamp, we get the hour. From the country, we can build a cross feature that crosses country and hour, because maybe the raw hour in UTC time isn't so much relevant as the hour in the country. So that's one thing we do. So that gives us a quick way to parse our raw data to get the features that we want to actually train on. Furthermore, we use what's called the hashing trick. So we don't train on the raw string, but rather a hashed version. So the final thing you see down here is the actual feature set that we train on. So when you hash features, there's a chance for collisions, but ignoring that, it turns out not to be such a big deal. We end up having 32-bit values as our features, which is incredibly useful for a number of reasons. First of all, we don't have to build some sort of dictionary key value lookup for a given feature what its weight is. Instead, well, it's still a key value lookup in the sense that your 32-bit weight corresponds to a value, but since they're just numbers from 0 to 2 to the 32, you can just store it in an array, which is a nice, simple data structure that is easy to carry around and easy to randomly access. Sorry, well, I just said this. And then also, this forces the dimensionality to stay fixed, at least until you increase the number of bits. So this is a common trick. I think Smola came up with it, or at least he said something like this when I talked to him. Okay. And also at the language level, what are we using? We like to use D. This is actually a language that Benoit liked a lot, and it's proven to be very useful. So basically, D, if you're not familiar, is like C with niceties on top of it. It's kind of like C++, what it would look like if it were created now. And so that gives us all the low-level power that we need from C, but also makes it relatively easy to quickly prototype. And of course, for a glue language, we use Python. It's a pretty standard language. We make heavy use of AWS services, EC2 instances to train our models. S3 is a general purpose storage to transmit files between our various instances and other teams. So the basic infrastructure looks something like this. We have our raw, so the bidder is external to us. It's bidding on the ads, and it's getting back the data, the raw impressions that we show, and then the raw clicks that we get. Those are stored in S3. So we have our joiner instance, which pulls those and joins them together to make the join logs like I showed you before, i.e. impressions labeled with a 1 or a 0 according as they click or not. We have a learner instance that grabs those and trains a model over those. So we have a prediction model, which the bidders grab and have at ready, which they use to make predictions, and the cycle repeats itself. So that's our basic infrastructure, right? But OK, so how do we know we're doing a good job? OK, so we want to assess our prediction accuracy. And so we need some sort of metric or some way to do this. There's a number of standard metrics people use. AUC is one of them. But since we care about the exact probabilities, again, we're bidding the exact probabilities. It's not like the probabilities are above a certain threshold, we go for it. If they're below, we don't. We bid a numeric value in proportion to it, right? So we found the average log loss is better for that. Honestly, they tend to correlate with one another, but average log loss, if you look into its derivation, has to do with the maximum likelihood estimator. So it's really tied to the actual values of the probabilities. We also do something which is kind of neat, which is, on any subset of traffic, we look at the average prediction, or our average predicted value, versus the actual click-through rate, like the observed label value, you could call it. So the idea behind this sort of mathematically is that if we were to predict perfectly, then if you get any subset of traffic, say, traffic in France, and we look at our average prediction in France, and then the actual click-through rate in France, they should be the same. Again, given enough data that it converges. But actually, kind of interestingly, conversely, if this is true on every subset of traffic, I would argue that you have a perfect predictor. Why? Well, in particular, you can talk about the subset of traffic where we predicted a 1% CTR. If it's true that we, on average, predict the actual value, then, well, 1% of the time, they would have clicked on that subset of traffic. But suffice to say, this, whether these two quantities are equal or not is a nice indicator if we're predicting accurately on a certain subset of traffic. And also practically, if we might be predicting well on average, but if we're like doing really poorly in one country, that could be bad for a customer who's primarily in that country. And then we have a nice little app we wrote using R, Shiny. Shiny is a little library for R that makes it easy to throw up a quick web app off of your analysis. And you can see here, I guess you can't really read it, but the bottom is our predicted probability, and the y-axis is the observed click-through rate. And you can see we're pretty accurate, right? This 45-degree line is perfect accuracy, and we're pretty close to it. So when we say somebody's got a 2% chance of clicking, empirically they do click 2% of the time. And we can also, you can't see it here because I had to hide some of our private information, but you can subset this to certain networks or to certain campaigns and things like that. Okay, so how do we backtest our model? How do we build the model itself? Well, we have a nice little web app I built out in Python Flask where you can launch EC2 worker instances, train models on the workers, accumulate the experiment metrics, and then provide visual comparison. So yeah, again, the key part here is it's a nice little web app where you can do this all. It makes doing it kind of fun as opposed to, sort of painful every time you want to get going. And so it looks kind of like this. You click to launch an experiment, and you fill it out, and you get your metrics back. The metrics come back like this. Again, I had to kind of hide some of our specific metrics, but you can see some of the less private metrics like our L1 norm of the weights, L2 norm of the weights, the SHAs of the various things, the various repos that we pull, things like that. So we do backtesting first, and then we say, okay, I see that adding these two features and removing this feature improves the model, so this model looks better than the one that's in production. Let's try to put it in production. Well, before we put something in production, we do live A/B testing. So we actually deploy both the production and a candidate model at the same time, and we shard traffic by cookie and send a fixed percent to the candidate predictor. And we have this app that goes over the A/B testing results. Again, hid some of the information here, but we can see, what is the click-through rate, what's CPM, CPC. These are all kind of ad tech terms, but basic metrics. So our infrastructure actually looks more like this. You can see that there's these kind of analytical ancillary jobs that sort of probe the pipeline as it's going through. Okay, so I've talked about this in very vague terms, and honestly, everything I've talked about is true no matter what you use for your model. I mean, at the end of the day, we're predicting probabilities, and we're either accurate or not, and we can talk about whether we're accurate or not, irrespective of what the actual model that's creating the probabilities is. But of course, we need to actually predict, so we need a model. So what do we use for click prediction? Originally, we used just basic logistic regression, and then an engineer, Matt Wilson, implemented and showed that it was better for us to use factorization machines. He actually wrote a great blog post about this you can check out. But I'll give you a brief overview of factorization machines here. So the idea behind factorization machines is it's sort of one level above logistic regression where you, in some sense, automatically include all second-order cross features. That's this, I don't know if there's a way to, oh, yeah. So if you were to have this be like a WIJ, that would be including all cross features. So it doesn't go that far, but instead what it does is it creates a k-dimensional vector of weights, VI, for every hash feature here, xi, and as this kind of extra term here, you take the dot product. So it's sort of like, you can think of the VIs as being a k-dimensional embedding of your features, and so the dot product is sort of how similar they are. So this is kind of like something between basic logistic regression and a logistic regression where you had all second-order cross terms. And if you look at this, the complexity, it seems, this part here looks like it's order n squared, but in fact, that term you can rewrite as such, and you can see here, after rewriting it mathematically as such, it's actually only order kn, and since k is relatively small, it's basically order n. And so we've experimented with that. We showed that improved average log loss pretty noticeably, so we've been using that ever since. We've also explored, okay, so that's the model we used, and how do we optimize it? We've explored various optimizers. The stochastic dual coordinate ascent, well, that actually only works for convex functions, and the factorization machine isn't convex, so that's out of the picture. But we did use that initially with logistic regression. SGD is very standard. LBFGS is a standard second order algorithm. But what we actually use now is Hogwild SQD. So Hogwild SQD is a variant of SGD where you basically perform SGD in parallel over a number of cores. And there's just one shared set of weight that they're updating as each one of them is processing a different instance. But normally you'd have to worry about like, well, one of them is reading while one of them is writing, and you have to coordinate, and that's a big pain. But here we just, I mean, well, not we didn't come up with the algorithm, but the way Hogwild SQD works is it just says, forget all that, just let them interfere with each other, don't worry about it, it's not a big deal. And it turns out, okay, so that of course gets rid of all locks in coordination, it lets it run really quickly, and it turns out empirically that it performs quite well too. Certainly when you take into account that you're allowed to use all your cores at full bore. Okay, so that's our basic click prediction algorithm infrastructure, but we also go beyond click prediction. So actually, once we have this whole infrastructure in place, we can really train any sort of predictor, right? Any sort of probability prediction. So we can reuse the infrastructure. So for example, well, customers actually, I said they care about clicks. Certainly they care about clicks more than ads, but even more than that, they care about conversions, right? They're trying to sell their product. They care that people actually buy their product. So we can use the following strategy to bid for conversions. So we bid a constant times the probability they click times the probability that once they've clicked, they go on to convert. It's called a post-click conversion, and most customers tend to care about those in particular because they can be directly attributed to us as opposed to, maybe we showed them an ad and then some other reason they bought it. So yeah, and the only missing piece here is this extra probability post-click conversion. So again, it's just given a click whether they convert or not. Very much the same problem, from a mathematical point of view, from a theoretical point of view. Of course, in reality, there's a bunch of additional challenges when you're trying to do conversion prediction. First of all, conversions themselves aren't like clicks where it's uniform across all. What is a click? It's very clear. You move your mouse over it, you click. Conversions mean different things to different people. Some advertisers, call it a conversion when you buy a product. Some of them call it conversion when you sign up for their mail. Some of them call it a conversion if you just visit their web page. So that's kind of a problem because when you're trying to learn a model, it can be wildly different proportions of conversions for the different advertisers. Overall, there's many fewer conversions compared to clicks, just because many fewer people buy things than actually click on an ad. Now, another big one here is conversions take up to 30 days after the click. So beyond that, our advertisers won't let us attribute it to them. But when we show an ad and somebody clicks on it, we technically have up to 30 days to get credit for it. And there's some subjectivity in determining what click even caused the ad, right? Because it's not like when you click, it's tied exactly to buying it. It's just that sometime down the line they bought something. Okay, so how do we get around these? Okay, so first of all, we have to join the clicks to the conversions. Like I said, we have clicks, we have conversions, but how do we match them up? Well, we're matching them up on the cookie, i.e. the user. So actually we use TrailDB, which Ville just talked about, because TrailDB stores our information by user. That's great because we're trying to join by user here. And we just iterate through 30 days worth of TrailDB information. And the heuristic we use, or the attribution we use, is we say a click followed by a conversion is a positive label. A click followed by another click, or the end of the trail, is given a negative label. So if you have a click, then a conversion, the first click doesn't get credit, only the second click. So it looks something like this. We have our cookie trail. It's actually a TrailDB that we iterate through. And you can see which clicks, this click here gets the credit for this conversion. And these other guys get no credit, or they're seen as not converting. Okay, so obviously there's some issues with this. Clicks towards the end of the trail are more likely labeled 0. They just haven't had time to convert. Well, we can fix this bias by doing a 30-day look-ahead window. So we could, say, okay, every click has to be given a fair 30 days to convert to label a 1 or a 0. But this is undesirable. First of all, that means that we have a 30-day delay in our data that we're allowed to train over. And that's particularly annoying because a new customer signs on and they want to get going right away. We don't want to tell our customer, hey, wait, come back in 30 days once we have your data. So instead, there's this paper by Olivier Chappelle, which uses what's called a delayed feedback model. And so we also have implemented this and found it to be productive. In fact, an intern, Bo, sort of pushed for this and developed the initial implementation, and then I built out the full implementation. So this is works as follows. Again, check the paper for the details, but the rough overview is we treat, so we just label our clicks as positive or negative, just as in this picture here, i.e. naively, namely the ones towards the end are more likely to be 0. But that's okay because we train an auxiliary model which predicts the click to conversion delay. So now we have a model that says for a given click about how long does it take for it to convert. And now when we train our model, we can weight our negative instances accordingly. So if this auxiliary model says that clicks happen really fast and we've had 1 day, we say, well, clicks happen pretty fast, we've had 1 day. Okay, if it hasn't converted by now, then we know it's not going to convert. But if our auxiliary model says, well, conversions take a while for this click, then if I say, well, this click's only had 1 day to convert and we know it takes a while, okay, there's some evidence that it's not going to convert, but let's not take it too seriously. And so, again, at the end of the day, what happens is the negative instances are weighted in accordance to how much time they've had to convert and how long the click conversion delay is predicted to be. Okay, another thing I mentioned earlier that we have to deal with is auction dynamics. So auction dynamics vary from exchange to exchange. So in the perfect world, everyone runs what's called a second price auction. The way a second price auction works is that the winner of the auction, whoever bids the highest price, pays the price of the second highest bid. And if you think about it for a second, this incentivizes you to bid your true value. Because if you bid higher than your true value, if you were already going to win, it doesn't matter. You'd still win, and you'd still pay the second price. You don't really get anything by bidding higher. If bidding higher would have caused you to win when you wouldn't have otherwise, then it's only because you eclipsed somebody else. But in eclipsing somebody else, you've now won something for a price that's higher than you actually wanted it. So that's not in your interest. And similar for lowering your bid. So second price auctions are great. It's kind of this gentleman's agreement where we're all going to make things nice and everyone's going to bid their true value. Well, of course, the auctioneers have incentive to try to get money out of people. So if they can convince you it's a second price auction but secretly have it be a first price auction or something else, then they can start to win until we catch on, and then we have this cat and mouse game. So some exchanges are doing pure second price auction, but in practice most exchanges don't. And that's not to say that they're dishonest. Obviously they can run it however they want, but as soon as you move away from a second price auction, you have to start using intelligence, and you can't just bid your true value. So for example, here's empirical data of what our bid versus win prices look like on a given exchange. I won't say who here, but you can see there's something awfully suspicious going on, right? It seems like a lot of the time when we bid something, we pay between 1 and 0.9 times our bid price. And that's not natural competition, right? That there's extra line here. So something weird's going on. And so, sometimes we can talk to the exchanges and get information. Sometimes they're less forthcoming, and we have to work with it regardless, right? So to get around this, auctions can also include hard floors. So sometimes they just set hard floors where if you bid below it, they just won't sell the inventory. That's to incentivize you to bid high. So they sort of make this threat that we have this hard floor, and if you don't bid high enough, you're not going to win it. So, you're going to therefore want to bid higher maybe. Soft floors they have the threat, but then if you bid below, okay, they'll still give it to you just for first price. There's also, we found out recently, multi-stage auctions where maybe there's a first round of bidding that's second price, and the winners of those go on to a first price auction. So there can be lots of weird stuff going on. And so to get around this, we train some additional predictors. We train a predictor that predicts the probability that we win the auction, and we train a predictor that predicts the probability that an auction is first price. And using those, we can bid more intelligently. I don't want to get into our exact details here because, like I said, it is kind of a cat and mouse game with the auctioneers. But in any case, these are just probability predictors, so they fit nice into our great infrastructure. Exact same A/B testing, exact same back testing, exact same automated deployment and everything. So once you have, it's like the 0 to 1 problem and the 1 to n problem. Once you've set up this great infrastructure, it becomes very easy to add additional predictors. Okay, so that's it. Do you guys have any questions for me? Yeah? Oh, why is it better than AUC? So that's kind of my personal opinion. I mean, in general, the two work in concert. So it's not really the case that we have a new model and it's like, oh, the average log loss is better, but the AUC is worse. Should we do it? Usually, if one's better, then the other is also better. But personally, the reason I feel it's more important than AUC is just fundamentally AUC is tied to this kind of thresholding idea where, you fix some threshold, and for all the probabilities above the threshold, you do something. For all the ones below, you don't do something. And then as you vary the threshold, what happens? And a good predictor, as you vary the threshold, traces out this nice curve. But we're not making this kind of binary decision. We care very much about our probabilities being accurate because we're bidding in proportion to our probability. And so really this picture here, this is what really convinced me we were doing the right thing, was when built out this app and actually saw that our predictions are pretty damn accurate. It's not like, so it's not even just that, as our prediction probabilities go up, the actual conversion rate or actual click-through rate goes up. It's really exactly equal, like we're exactly predicting dead on, and that's what really matters. For example, if this graph were to have a slope of 2 instead of a slope of 1, the AUC would be exactly the same because the thresholds would all be the same, and yet that would be horrible for us because our predictions would be off by a factor of 2. So it's, in the case when you care about the actual probability values, then the average log loss is a better metric.
Probably that's about it in terms of time, but our speakers will be available after the talks around, right?
Okay, well, yeah. Thanks for having me.
Thank you so much.